now we have the same three cases we had before. First case is when we had real distinct eigenvalues. So that means each eigenvalue has an algebraic multiplicity of 1. And we deal with this the same way as before. So same as before. So let's say our eigenvalues are lambda 1, lambda 2, all the way to lambda k. And all of the eigenvalues need not be distinct, only the ones we're talking about. So we could have other repeat ones, but we're going to talk about how to deal with the distinct ones that we do have. So find the eigenvalues, find the eigenvectors v1, v2, all the way to vk. And our solutions have the form yj equals e to the lambda jt times vj. And our total solution takes the form c1 e to the lambda 1 t v1 plus c2 e to the lambda 2t v2 all the way to ck e to the lambda k t vk. So same as before. Now we can move on to our next case. So complex eigenvalues. So these will always, if our matrix has real entries, which they always will, these will always come in pairs. And these pairs will be conjugates. And to go over it, remind you what conjugate is. If we have lambda equaling a plus bi, then we'll get another solution, or another eigenvalue, which is a conjugate a minus bi. So it just has a negative imaginary part than the other one. So this is exactly what happened in the 2x2 case. So same as before. We take one of the two eigenvalues. We use that to find a complex eigenvector. So this eigenvector, I will call it W. So we find that by looking at the equation a minus lambda I times W equals 0. So the null space of a minus lambda I. And this W will have a real part. We'll call it V1. And it'll have an imaginary part, V2. And we use this complex eigenvector to find a complex solution, which we call z of t, which equals e to the lambda t times w. And then this will have a real part, and it'll have an imaginary part. So this is one solution, and this will be the other solution. And these are guaranteed to be linearly independent of each other. So for each pair of complex eigenvalues, we get one pair of linearly independent solutions. So this is the same as in the 2x2 case. So now we go to our third case. and that's the case of repeated real eigenvalues. So, like before, if the algebraic multiplicity of the eigenvalues equals the geometric multiplicity, and that means that the dimension of the null space of A minus lambda I equals the same as algebraic multiplicity, then we know how to deal with this. We get, let's say our algebraic multiplicity equals Q for our eigenvalue. That means we'll get Q linearly independent eigenvectors, and each of the solutions will be e to the lambda t v1, and then y2 will be e to the lambda t v2 all the way to q, which will be e to the lambda t vq. So yeah, these eigenvectors will be v1, v2 all the way to vq. So yeah, if we have q different, if our algebraic multiplicity is q, we need q different eigenvectors. If we don't, so if the algebraic multiplicity is greater than the geometric multiplicity, that's the only other case, we need to use a mathematical tool called matrix exponentials, which is the topic of the next video, so we can't cover that yet. But this just goes to show that dealing with higher dimensional systems just involves applying what you learned in 2x2 systems. Physical